All right, stats. Here we are for a stats chapter 11 video that you may or may not have to watch. Okay. If you're watching it, you probably got it in an email. Anyway, we are brought to you by in-house sponsors. First off, Laura Bar for Kids, gluten-free. My little ladies love these bars though, so not for dad. Next up here, RX Bar. Look at that, 12 grams of protein. The body is a temple. My wife also loves this flavor, so I get the dark chocolate ones instead. But this one is for me. This is Noon Sport Hydration Strawberry Lemonade. All right. Want to get that water a little extra light, a little extra electrolytes. All right, you're the fourth video here. I am prepping, so hopefully I don't get too tongue-tied. Anyway, folks, ever find yourself on that 2-hour run? Yes, you do. Get a little tired, get a little lightheaded. What does the body need? Goo. That's right. Hammer gel raspberry goo gel. All right, excellent. Chapter 11 notes here. I want you guys to look at the bottom of page 9. This is in your note packet. You're going to write a few things as well. But the bottom of page 9 says something really important. The central limit theorem. The facts about the mean and the standard deviation of X bar are true no matter the shape of the distribution. But what is the shape of a sampling distribution when the population is not normal? It is a remarkable fact that as the sample size increases, the distribution of X bar changes shape. It looks less like that of the population and more like the normal distribution. Oh my gosh, so when the sample is large enough, you know, some say even 30, but like definitely 50, most definitely 100, then the distribution of X bar is very close to normal. That is crazy, folks. So it doesn't have to come from something that is normal for us to apply the central limit theorem. Okay, very, very big deal. Because now we're going to have questions where you don't see the, like X is approximately normal. We're going to have questions where you don't see that. So let's take a look here. Central limit theorem is this. Draw a simple random sample of size n from any population with mean m and finite standard deviation. All right. Sigma. So the central limit theorem says that when n is large, the sampling distribution of X bar is approximately normal. So that is very important. It allows us to use the normal probability calculations to answer questions about sample means from observation, even when that is not normal. The population is not normal. That is a big idea. All right, so yeah, this is talking about household earnings in thousands, and this is just the general distribution. This is obviously not normal, right? Like this, has a little bit of a bell curve look if we isolated this, but that's way skewed to the right. All right, so if I did a bunch of samples of size 100, look at my sampling distribution. That's starting to look pretty normal, all right? Anyway, let's take a look at a question. Let's go to page 13. Going to page 13, and we're going to look at both 1112 and 1113. Just going to do a few examples here. Detecting gypsy moths. The gypsy moth is a serious threat to oak and aspen trees. Shout out to Ag here. And is that botany? Anyway, a state Ag department. Oh, big Ag. Okay, so Ag folks, you know who you are. Very good. Shout out to you guys on this one. Places traps throughout the state to detect the moths. When traps are checked periodically, the mean number of moths trapped is only 0.5, but some have several moths. Okay, so the distribution of moths is discrete and strongly skewed, with a standard deviation of 0.7. But sample size 50 is going to be good enough. So what are the mean and standard deviation of the average number of moths in 50 traps? So X bar is approximately normal, with a mean of mu and a standard error of sigma over root n. All right, so what is your standard deviation sigma? 0.7. What's the square root of 50? Now, I did not have my regular calculator handy here. I used a little phone calculator, so let's just check that again. I'm feeling pretty good about it. Yeah, I rounded. You want to round this to 3 decimals because you're dealing with a pretty small standard error. So we're going to call it 0.099. So X bar is approximately normal with a mean of 0.500 and a standard error of 0.099. Okay, so B says, what is the probability that of those 50 traps you have a mean that is greater than 0.6? I'm going to call it 0.600. So this is the formula we're using. We're saying Z is X bar minus the mean over sigma over root n. That's the standard error. So Z is equal to 0.6 minus 0.5 over the standard error. Again, I don't need to rewrite this as I've already found it. 0.099. That is 101. I didn't have a Z table on me, but folks, you have the interwebs too. You can Google Z table PDF, and the first one I saw was from the University of Florida. That's the one you have in your possession. So then I found it, and that is 8438. So I'm going to do 1 minus 8438, and that's 1562 is my probability. 1562. Okay. Pretty cool there. Standard error. 099. All right, then we're talking about 1113. Then we're going to go to page 14. We're just going to do that page, and we're going to be good. 1113 says it's the one that's more on insurance. An insurance company knows that in the entire population of millions of homeowners, the average annual loss from fire is $250, but the standard deviation of loss is 1,000. The distribution of losses is strongly skewed. Most policies have a $0 loss. But if you have large losses, okay, yeah, so that's like if anyone has fire insurance. A lot of times you don't use it, you know. We've had homeowners insurance for a long time, 12 years, and we've only had to use it twice. Now, in those 2 years, it's been an okay amount, so that's how it works there. If the company sells 10,000 policies, can it safely base its rate on the assumption that its average loss is going to be no greater than $275? Question. All right, so no greater than means I want to know the probability that X bar is less than or equal to 270, given that N is 10,000. All right, so let's find the sampling distribution. It didn't ask for that, but I just want to do it here. X bar is approximately normal with a mean of 250 and a standard error of 1,000 over square root of 10,000, which gives me 10. That's pretty cool because the square root of 10,000 is 100. Okay, so then I'm going to say Z is X bar minus the mean over the standard error. I had this flipped accidentally. So that's a positive 25 over 10. So that's a positive 250. If you look up 2.50 in your Z table, you get 9938. So what's the probability that X bar is less than 275? It is 9938. So there's a 99.38% chance that the average loss is going to be at 275 or smaller. So yes, they should feel very good that they should expect this or less. Feel pretty safe about that. All right. Anyway, let's take a look at page 14, and then we'll stop at 14. We will pick this up, and then we will finish these notes relatively soon next week, possibly by the end of class on Wednesday. Your homework set is not due until the 22nd. You will have an in-class assignment, though, next Friday, the 17th. The Bureau. There you go. You know, that one gets me. Of Labor Statistics announced last month that it interviewed all members of the labor force. So it didn't. No, it sampled 6,000 households, which is a lot. Our margin of error is going to be microscopic. 4.9 of the population were unemployed. So the bold-faced number is not a parameter. They didn't interview everybody. There's more than 60,000 households. It is a statistic. It is a very useful statistic, but it is a statistic. All right, a study of voting chose 663 registered voters at random. That's definitely a stat. Okay, so 72% is most definitely a statistic, but that's not the bold-faced letter. It's 56% of registered voters. Registered voters is the population of voters. That's everyone that's allowed to vote. So 56% is, in fact, a parameter. 72% is a statistic because it comes from a smaller sample. But 56% of registered voters, that is everyone that is allowed to vote. Now, annual returns on more than 5,000 common stocks available to investors and vary a lot. The mean return was 8.3%. It is usually around 8%. The standard deviation, though, is huge. So the law of large numbers, guys, if you go back to the top of page 4, the law of large numbers is all about X bar approaching the mean. So C is sounding pretty good for like central limits stuff, but in terms of what the law of large numbers means, it does mean this. As you invest in more and more stocks chosen at random, your average return on these stocks gets ever closer to 8.3. That is very true. The law of large numbers did not talk about the normal distribution, so like that would be more of a central limit theorem thing. All right. Scores on the math part of the SAT exam in a recent year were roughly normal with a mean of 515, a standard deviation of 114. You choose a simple random sample of 100 students and average their SAT math scores. If you do this many times, the mean is going to be 515. That's because X bar is normal with a mean of the population mean and a standard error that is different. So the mean is still going to stay 515. But if you do this many times, if you have a simple random sample of 100, what is going to be the standard deviation of these average scores? And that's when you take 114 and you divide it by the square root of 100, which is 10. 114 over 10 is 11.4. 11.4 is your answer there on 1118C. All right, so this is a sort of quick video. We just did a few examples, and then page 14 here, and that sets us up perfectly for Monday. All right, folks, have a good weekend. I will see you on Monday the 13th when the weather is better. This is Yak Math Videos signing out.